So you see the difference, 22 orders of magnitude difference between a good conductor and a good insulator. And if I make this potential difference over the wire, if I make that 1 volt, and if I apply Ohm's law, V equals IR, then I can also calculate the current that is going to flow. If IR is 1, then the current here is 100 amperes, and the current here is 10 to the minus 20 amperes. An insignificant current, 10 to the minus 20 amperes. I first want to demonstrate to you that Ohm's law sometimes holds. And I do a demonstration whereby I have a voltage supply. I put a V in here. And we change the voltage in a matter of a few seconds from 0 to 4 volts. This is the plus side. This is the minus side. I have connected it here to a resistor, which is 50 ohms. We use this symbol for a resistor. And here is a current meter. And the current meter has negligible resistance, so you can ignore that. And I'm going to show you on an oscilloscope. We've never discussed an oscilloscope, but maybe we will in the future. I'm going to show you there projected the voltage, which goes from 0 to 4, versus the current. And so it will start here, and by the time we reach 4 volts, then we would have reached a current of 4 divided by 50. According to Ohm's law, I will write down just 4 divided by 50 amperes, which is 0.08 amperes. And if Ohm's law holds, then you would find a straight line. That's the whole idea about Ohm's law, that the potential difference is linearly proportional to the current. You double the potential difference, your current doubles. So let's do that. Let's take a look at that. You're going to see that there. And I have to change my lights so that you get a good shot at it. Oh, it's already going. So you see, horizontally, we have the current, and vertically, we have the voltage. And so it takes about a second to go from 0 to 4. So this goes from 0 to 4 volts, and you see that the current is beautifully linear. Yeah, I'm blocking it. Oh no, it's my reflection. That's interesting. Ohm's law doesn't allow for that. So you see how beautifully linear that is. So now you may have great confidence in Ohm's law. Don't have any confidence in Ohm's law. The conductivity, sigma, is a strong function of the temperature. If you increase the temperature, then the time tau between collisions goes down because the speed of these free electrons goes up. It's a very strong function of temperature. And so if tau goes down, then clearly what will happen is that the conductivity will go down. And that means rho will go up. And so you get more resistance. And so when you heat up a substance, the resistance goes up. Higher temperature, higher resistance. So the moment that the resistance R becomes a function of the temperature, I call it a total breakdown of V equals IR, a total breakdown of Ohm's law. If you look in your book, they say, oh, no, that's not a breakdown. You just have to adjust the resistance for a different temperature. Well, yeah, that's an incredible poor man's way of saving a law that is a very bad law, because the temperature itself is a function of current. The higher the current, the higher the temperature. And so now you get a ratio V divided by I, which is no longer constant. It becomes a function of the current. That's the end of Ohm's law. And so I want to show you that if I do the same experiment that I did here, but if I replace this by a light bulb of 50 ohms, it's a very small light bulb. Resistance, when it is hot, is 50 ohms. When it is cold, it is 7 ohm. So R cold of the light bulb is roughly 7 ohms, I believe. But I know that when it is hot, it's very close to the 50 ohms. I think it's a little lower. What do you expect now? Well, you expect now that when the resistance is low in the beginning, you get this, and then when the resistance goes up, you're going to get this. I may end up a little higher current because I think the resistance is a little lower than 50 ohms. And if you see a curve like this, that's not linear anymore. So that's the end of Ohm's law. And that's what I want to show you now. So all I do is here I have this little light bulb. For those of you who sit close, they can actually see that light bulb start glowing, but that's not important. I really want you to see that V versus I is no longer linear. There you go. And you see every time you see this light bulb go on, it heats up, and during the heating up, the resistance increases. And it's the end of Ohm's law for this light bulb, at least. It was fine for the other resistor, but it was not fine for this light bulb. There's another way that I can show you that Ohm's law is not always doing so well. I have a 125 volt power supply. So V is 125 volts. This is the potential difference. And I have a light bulb. You see it here. That's the light bulb. The resistance of the light bulb, cold, I believe, is 25 ohms. And hot is about 250 ohms. A huge difference. So if the resistance, if I take the cold resistance, then I would get 5 amperes, but by the time that the bulb is hot, I would only get half an ampere. It's a huge difference. And what I want to show you, again with the oscilloscope, is the current as a function of time. When you switch on a light bulb, you would expect, if Ohm's law holds, that when you switch on the current, or you switch on the voltage, I should say, that you see this. This is then your 5 amperes.